Can you all see my slides up on the screen?
Just a moment, please. Yes, go ahead, Mehmet.
Thank you, Dina. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. Good evening. We are delighted to have Dr. Eric Wolf as our guest speaker this evening. Dr. Eric Wolf is a research scientist at the University of Colorado, Laboratory for Atmospheric and Space Physics. Eric has graduated from the University of Maryland in 2007 with bachelor's degree in astronomy and graduated from University of Colorado in 2014 with a PhD in atmospheric and oceanic science, focusing on 3D climate modeling of the ancient Earth, which might be interesting to talk about as well. In his professional career, Eric has applied his original academic love for exotic planets with his technical skills as climate modeler to explore the wide-ranging theoretical possibilities of the strange new worlds that lie beyond, i.e. the exoplanets. Eric lives in Golden, Colorado with his wife and giant schnauzer and enjoys the typical Colorado fare of skiing, mountain biking, hiking, and taking long weekend trips into the mountains. So Eric, please proceed with your presentation.
Thank you for the nice introduction, Mehmet. And thank you everybody for having me here today. Thanks for sticking around on a Friday night. So the title of my talk is A Multiplicity of Worlds. So a little brief about me, which you already kind of heard. First of all, sorry, my lighting isn't very good in my computer room right now, so I know it looks kind of dark. But so who am I? Well, you've heard most of this. So this doesn't really bear repeating. I will kind of skip down to my research interests. So while this is in the Denver Astronomy Society, what I do is I'm a theoretician and I work with climate models, 3D climate models, like the type that are used to predict climate change, but I apply them to alien worlds. It started with thinking about the early Earth and then thinking about other planets in our solar system and then onward to exoplanets and thinking about habitability. So I can't answer your astronomy questions nor pick out stars in the sky, but I can tell you a lot about the theory behind our thinking about extrasolar planets. So as you all know, when you look out into the night sky, there are perhaps thousands of naked eye visible stars in the sky, but that is a gross underestimation of the total number of stars in the universe, which is something like 10 to the 22nd or 10 trillion billion stars. And to the best of our knowledge, from what we found in our initial surveys looking for planets and from our best theories, we think that probably every star has planets. There's no reason why they shouldn't. We see exoplanets everywhere we look, and we know from how stars form and stellar systems form that planets should be everywhere. So in our initial surveys, we've already found a dazzling variety of worlds, starting from when the first exoplanet was discovered in the mid-90s, onwards today through the Kepler Space Telescope and the TESS telescope, which have really done the heavy lifting in finding these planets. So with the most recent update, when you look at the NASA Exoplanet Archive, there have been 5,054 confirmed extrasolar planets today, found primarily through two different methods. The first one on your left, the radial velocity method. And this is, so, gravity, the sun pulls on the Earth and the Earth pulls on the sun. So the sun actually wobbles just a little bit, actually more so mostly from Jupiter's influence on the sun. So seeing this radial velocity shift when we look at stars, we can detect planets orbiting around them. And then the other way, the main way that we can detect extrasolar planets is through transit photometry, where we can see a planet, if we're viewing the stellar system in line, which is a small probability, but there's so many stars out there, so it happens. We can see the shadow of the planet move across the star, so we see a periodic dip in the star's brightness. So we don't, except in very rare special cases, we don't observe extrasolar planets directly. We see them indirectly through their effects on the star's light and from the gravitational effects, which itself we see via the star's light being periodically redshifted and blue shifted through its wobble. So unfortunately, there is a large observational bias in the way we observe extrasolar planets, and the bias is for the detection of large planets which orbit close into their stars. So larger the planet, the bigger the gravitational impetus on its host star, the bigger the shadow it casts as it crosses in front of its host star. But you can see in this plot here, where on the y-axis it is the period in days of the planet, and the x-axis is the period in days, the y-axis is Jupiter masses. And this, the lines I've drawn on here is where an Earth mass, Earth period planet would be. And you see the bias is into this upper quadrant for larger planets, much larger planets, even larger than Jupiter, which orbit on very short periods, much less than an Earth year. And if we look at this a different way, we still have period on the x-axis. We have the irradiation relative to Earth. That's how much energy the planet receives. So, and I've drawn on the Earth stellar flux line. So if we're looking for a habitable-like planet, we think it would have near Earth-like stellar flux received values. And because of this bias towards observing planets that are much closer into their host star, you can see the majority of planets we've observed to date are at high stellar fluxes. And so we don't expect these trends to be the actual reality. These are our strong observational biases about how it's possible for us to observe and detect extrasolar planets. So, but already we found this large diversity of new planets that challenge our understanding of how stellar systems are formed. And we have new types of planets, and you can see here hot Jovians or hot Jupiters, Jupiter-sized planets that orbit only a few periods of only a few days, so they're extremely close to their sun, several thousand Kelvin. We didn't think that would be possible for planets like that to exist and maintain such massive hydrogen atmospheres. Also, we found a lot of planets that are between the Neptune class worlds and terrestrial worlds. They're sort of in between sub-Neptunes or mini-Neptunes and super-Earths. We don't really quite know what to make of it. But right now our bias and observations are into this quadrant as well of these larger, hotter planets down into the sub-Neptune regimes, where you see Earth down here, if you can see my cursor. The terrestrials are challenging for us to work with at the moment through observations. So of course, it needs some introduction with the James Webb Space Telescope, with the first images being returned. When we think about exoplanet science, James Webb is going to revolutionize our understanding of these gas giant type planets, these hot Jupiter type planets. It's going to be able to get really good spectra, and both in transmission and emission spectra, and really help us understand the physics of these worlds. So, in probably the most overlooked image of JWST, what got most of my colleagues the most excited was this one here, which is a transmission spectra from WASP 96b, which is a hot Jupiter with a temperature of about 1,000 Kelvin, which is about 1,800 degrees Fahrenheit. And you can see the wavelength on the x-axis, and then the spectra on the y-axis measured in parts per million. That's the amount of light that is blocked by the atmosphere. On the next slide, I'll explain a little bit better. But in this spectra, all the dots are the James Webb points, and then the blue is a modeled, from the retrieval of the data. And you can see that they've identified water vapor in its atmosphere, in this planet's atmosphere, and the flatness of the spectra in this region where my cursor is indicative of clouds in the atmosphere. And it should be noted that this was taken on, and I talk about this a little later, on one transit, so only about 2 hours of observing time to get this really interesting transmission spectra from WASP 96b. Of course, this was sort of a cherry-picked case. It was a case chosen that was going to be very amenable to these observations on first go. I'll come to that a little bit later when I circle back into terrestrials. So just a quick interlude, transmission spectroscopy. How does it work? What do I mean by this? So in the foreground, in the background here, you have your star. In the foremost ground here, you have your instrument, your telescope, and this is the planet that you're observing. And what happens is the starlight, as the planet moves in front of the starlight will permeate through the annulus of atmosphere around the planet. So the atmosphere, the molecules in the atmosphere will filter out the light of the star as it travels through the atmosphere into our detector. So based on the absorption lines that we see, we can determine, oh, is that water vapor absorbing in the atmosphere or carbon dioxide absorbing in the atmosphere or perhaps even clouds, which is really tricky. So that's how we, through this process of transmission spectroscopy, is how we observe or try to characterize the atmospheric constituents of extrasolar planets. You can think about it sort of like a terrestrial Earth-based limb sounders when we're monitoring pollution and different constituents of the Earth's atmosphere that look at the sun and scan through the setting sun through the atmosphere of Earth. It's the same principle except with extrasolar planets. So, but a bigger, more challenging goal in these hot Jupiters is actually Earth-similar and potentially habitable extrasolar planets, which the theoretical work behind JWST that has come out to date indicates that Webb is going to struggle to get these nice characterizations of Earth-similar planets. So you may be aware of the recent decadal survey, which is planning the next grand space telescope is going to be designed specifically to look at Earth-like extrasolar planets. If you think about it, the design phase for Webb was 30 years ago, where exoplanets wasn't even a glint in the designer's eye. So it's being retro-purposed to think about extrasolar planets. Now that's the hottest topic, one of the hottest topics in astronomy. So the next grand one is going to be designed specifically with habitable exoplanets in mind. So, and the spot I showed before, it's really this region down here when you get into the habitable zone. So to date, there still have been about 21 targets identified, exoplanets identified as potentially habitable exoplanets based on more conservative definitions. Don't need to go through all of these. Some of these are so far away that they don't really make good follow-up targets. The Kepler field was very narrow but very deep and went out about 1,000+ light years. So those don't make good follow-up targets for characterization. We're really looking at these planets about 40 light years and less. TRAPPIST, which I'll talk about later, and less make good targets for follow-up characterizations. So, as you've probably seen in your favorite mainstream media source, you'll see these sensational articles saying, an Earth-like planet has been found. And well, we need to be very careful with our language. This kind of frequently comes up in the science community now. And scientists are 100% just as guilty as some of these science media articles out there as well, because you'll see peer-reviewed articles saying a temperate planet has been found in the habitable zone. So just like the mainstream science media fishes for page clicks, respectable scientists fish for citations with sensational headlines as well in their articles, because what we really know to date about temperate planets found in the habitable zone, they don't look like the artist's image here, but they actually look more like this. So we know the radius of the planet with an uncertainty, the mass of the planet with an uncertainty. We know the stellar flux received by the planet with an uncertainty, and the spectra of the star. Actually, I'm going to peel away the atmosphere here because we don't even really know if they have an atmosphere or not. It's just an orb in the sky. So when you see those articles about the next Earth-like planet being found, read them with caution. There's a lot of uncertainty and a lot of theory that comes in afterwards that people like myself have worked on. So you may have, the word habitable gets thrown around a lot, almost too much in the field that it's become a loaded term. So, but we can think about it in terms of Earth. Earth is the only habitable planet that we know. And we know that water is the key to life. So that sets our basic foundation to thinking about searching for an exo-Earth. So we think of a habitable planet as an ocean-covered planet. So that starts to give us some constraints. We know that it has to be somewhere between the freezing point, so it's not all ice, or the boiling point, so it doesn't, I skipped ahead one, whoops. Boiling point, so the water doesn't evaporate. Now, of course, there's caveats to this. There's extreme niches for life. We find life in the dry desert heat of the Atacama, where there's virtually no water, or in the boiling pots of Yellowstone, or beneath the glacial ice of Lake Vostok, completely detached from the atmosphere. So the habitable zone isn't to say it's the only place where life can exist. We can envision habitable worlds that don't fall within our picture of an ocean planet, such as a dune-like world, or beneath the ice of Europa or Enceladus, or in the methane lakes, which we observe on Titan, or perhaps even in the boiling volcanic sulfur conditions of Io. So the life, I know is, I think, a cliche quote, I think it's from Jurassic Park, but life finds a way. So we shouldn't underestimate where niches for life can take hold. But for our purposes, we seek broadly habitable surface environments. And why is that? Well, if you're looking deep into space with a grand telescope, in order to actually detect life, you need life to be abundant at the surface, so much so that it can modify the planet's atmosphere and produce so-called biosignatures or even technosignatures, so we can actually detect it. You can't detect a change in a planet's atmosphere if life exists below an ice shell, so to speak. Or there are scant microbes on a desert planet that don't really affect the larger climate. But with Earth, for instance, the rise of oxygen came with the onset of photosynthesis. There's the biological mechanisms that produce chemistry, disequilibrium chemistry, where oxygen and methane coexist together when they shouldn't. Or if you look at the Earth now, we see waves of CO2 based on the seasons and the respiration of plants and the seasonal difference between the north and the southern hemisphere and the obliquity of the planet. And things like that are only detectable when you have abundant life on the surface. So that brings us to the famous concept of the habitable zone. So the habitable zone has become kind of a buzzword in the community that is more controversial than it should, because some will wring their hands and say, well, it's not really fair because you can have all these exotic niches for life. So you can have habitable planets outside the habitable zone, or you can have planets in the habitable zone that aren't habitable. So we need to be more clear with our language about it. So a better definition, or at least I think a more complete definition, is the habitable zone is the area in a solar system as measured by the distance from the host star where a terrestrial type planet could potentially have abundant liquid water on its surface if the planet has the proper balance of atmospheric gases and condensates available to support an appropriately stable climate. So the habitable zone is really a search zone. It's where our best thinking about how the geophysics of planets work would say, okay, if I have to look in a certain region, the probability of an Earth-sized planet being able to have a nice climate and maintain life is within this habitable zone. That's not to say the planets in the habitable zone are habitable or that you can't have life outside the habitable zone. But if you have one shot or 1 hour to point your telescope, where are you going to point it? You're going to point it to something in this higher probability region to look for life. So the theory behind the habitable zone, we can all see the groundwork laid in our own system when we look at Venus, Earth, and Mars, 3 relatively sister planets. So Venus, hand-wavingly, too close to the sun and too hot. Mars, too far away from the sun, too cold. And Earth, of course, the third bowl of porridge. It seems to be just right. But this is, a gross kind of simplification of the picture of what's going on here. There's actually complicated geophysics going on. So the sun, all stars evolve in time. All stars grow brighter with time, depending upon their stellar type. And then atmospheres evolve in time. There's atmospheric loss processes, which depend on the size of a planet or if the planet has a magnetic field, how active the star is, things like that. And then the atmosphere can also be modified through volcanism, which depends heavily on the geophysics of the planet and how tectonically active the planet is. Modification through biology, which I just mentioned for Earth, has happened. So we can start to characterize the geophysics of these habitable zone boundaries by learning from our nearest neighbors, Mars and Venus and beyond, which aren't habitable, and then also compare with Earth. So early Venus, there's evidence in theoretical thought that early Venus may have been the first habitable world. So there's measurements of the hydrogen isotopic ratios in the upper atmosphere of Venus lend to the belief that it once had a large amount of water that was lost to space. So it had water, but it's gone now. Modeling, where you combine a weaker early sun, combined with modeling indicating a very cloudy climate due to Venus's slow rotation rate, indicate that early Venus could have been habitable. But then as the sun brightened, you enter into the runaway greenhouse effect, where water vapor, which is a strong greenhouse gas, starts to trap in more energy and cause the climate to get warmer, and then you get more water in the atmosphere and so on and so forth until the planet becomes unbearably hot and the water boils away and is lost to space. And then so that's what we think happened with Venus. And then there's a couple of extra steps until you get to Venus today. So you lose the water to space, the planet becomes totally dry, and then without any water, you lose the carbon cycling processes. So volcanism builds up a dense CO2 atmosphere, which you see on Venus today. So we can trace the geophysical evolution of Venus as sort of a quintessential beyond inside the inner edge of the habitable zone type world. So the inner edge, we canonically say is marked by planets that go into a runaway greenhouse and lose their water. So on the outer edge, we can start to think about Mars. So Mars famously also has much evidence for liquid water, only made possible under a very dense greenhouse. Mars is much further away than Earth. It gets about 40% of the stellar flux that Earth does, and it got even less in the distant past due to the weakness of the young sun. But we know with a dense CO2 atmosphere mixed, the leading thoughts now mixed with hydrogen gas as well, probably outgassed from volcanoes. So this dense greenhouse was able to maintain a habitable early Mars much, much further away than Earth. So we know it's possible that you can have a habitable planet that's much further away from a star and much less stellar energy than the Earth. Mars, though, lost its atmosphere also, but for different reasons than from Venus losing its water. So Mars is small, it has no magnetic field. So the stellar activity of our own star slowly has stripped away the atmosphere of Mars over time. It was too small to retain it. So Mars became dry like it is today. And then we can think about Earth, of course. So Earth has been continuously habitable for virtually its entire lifetime, despite the sun having increased in brightness by about 25%. So why is that? That's been made possible through, oh, I got ahead of myself. So we also know that the Earth, though, has gone into so-called snowball Earth events, where it's become completely frozen solid with ice. All the oceans were frozen solid. But then each time the Earth was able to recover, and this was due to an active carbon cycle. So CO2 has been regulated through plate tectonics, outgassing of volcanism through volcanoes, burial of CO2 at subduction zones. So this active carbon cycle has served as a bellwether to moderate CO2 through time. So as the sun has gone from weak to stronger, CO2 has gone from high to low and moderated Earth's climate. But of course, there's at some points, this mechanism has gone off the rails and ended up in snowball Earth events as well. And then finally, we can think about the icy moons of the outer solar system. Europa, Enceladus, Ganymede, which have a lot of water on them, but they are frozen solid and they have no atmosphere. So that tells us there is a limit in the solar system where you go too far out and you're not going to be able to warm a planet, that it will just be frozen solid. So the outer edge of the habitable zone is marked by this runaway glaciation point where the whole planet freezes solid. And this is where a contrarian would say, well, you can have life, in hydrothermal vents underneath the ice. That is true, 100% true. Nobody's denying that. But if you're looking through a telescope, 40 light years away, you're not going to be able to see those hydrothermal vents 4 kilometers below the ice shell modify an atmosphere and detect anything from it. So that's why we set that limit of our habitable zone, our CERC zone, to be a frozen world at the outer edge. So we can go back to considering our extrasolar planet again. We don't know much about it. We know how much, the stellar flux, which, we derive from the distance from the star, from orbital geometries. We know the period, and we know the mass of the star and the mass of the planet. And then from the stellar spectra, which can change wildly between a M-dwarf star, which we'll talk about later, to the brighter type stars, G, F, and beyond. So we know how much energy the planet's receiving. There are 2 big unknowns, though, at the moment, which we hope to do better on with future instruments, are what is the atmosphere and what are the surface properties, because these are the missing pieces that will determine everything. So like I said, with Earth, there are times where the carbon cycle broke down and the Earth turned into a snowball. So the difference between the Earth being at times habitable and a frozen uninhabitable snowball was just the CO2 content. So it is these unknowns which are our great challenge to try to observe and characterize through spectra. But in the meantime, there's been a lot of work, and this is what I work on, is the theory behind it. So we use numerical climate models to fill in the missing pieces, using plausible parameters to constrain the possibilities for the atmosphere and the surface properties, which we don't know about. So we resolve these gaps through modeling, through climate modeling. And a climate model combines all these different aspects of a climate system, from where clouds and aerosols are like dust and volcanic ash and things like that. And the dynamical core, which tells you which way the wind blows, and the radiant transfer, which is, in my opinion, one of the most important parts. It tells you how the sun's energy filters into the planet and how the greenhouse energy filters out. Then you've got issues of convective processes and surface processes and ocean processes. And we combine all of these things together into a self-consistent calculation of climate. So we do this for Earth today, and our climate models have proven to do very well at predicting, unfortunately so, at predicting climate change. The dire predictions have proven to be accurate from models of the past, predicting into the now. This is my tool of choice, is to use these climate models as well to simulate how exotic climates react on other planets in the universe. So We can model any generic planetary climate and their evolution by simply changing a few things. So we can change the surface, take a generic climate model, and we can change the boundary conditions and continents, ocean, glaciers, albedo properties, soil properties, topography. So these are unknowns when it comes to extrasolar planets. So usually what we do is we choose idealized end member points. It's either entirely ocean covered or entirely land covered. So we can try to bracket reality, if that makes sense. And then we have the geophysical properties. You have your mass, your radius, your surface gravity. These are all knowns. We know these from observations. And then you change your atmospheric composition. So the total pressure, the amount of greenhouse gases, the amount of condensable species, like water vapor can form clouds, for instance. So these again are unknown. So we'll choose a range of plausible values from very little atmosphere to thick, dense atmospheres to give us a range on what reality may be. And then we have changing your stellar input. So it's not the sun spectra at 1360 watts per meter squared, but you have some different star that has a different spectra, different stellar energy distribution, and a different distance from that star gives you a different total flux of the planet. So these are knowns. We know these from observations. And then changing the orbital properties of the planet. So these are both a mix. Some of these are known, some of these are unknown. From observations, we know generally the length of the year and the eccentricity of the orbit. Obliquity is something. Obliquity and rotation rate are question marks. So around sun-like stars, those are unknowns, but around M-dwarf stars, which are the top candidate systems due to observational biases, the planets tend to be tidally locked, like the moon to the Earth, where the same side of the planet always faces the star, the same side of the moon always faces the Earth. And the obliquity gets damped down to very low, and the rotation rate matches the orbital period. So in those limits, we do actually know the obliquity and the rotation rate that we have to plug into our models. And then there are advanced properties that are calculated by the models, things like ocean heat transport, photochemistry, aerosol layers. I could throw in other things from that GCM slide that are calculated by the models. You set up the atmosphere, you set up all these other parameters, and clouds are self-consistently calculated, and other things as well that come out of the model calculations. So by capturing all these complex processes, GCMs are well suited to simulate alien worlds. So any given planet in the habitable zone, based on what exactly the atmosphere is, which is unknown, could be such a wide variety of things, from cold, thin atmosphere Mars-like worlds to icy worlds to Earth-like to hot planets to dry planets. So our goal with modeling is to try to simulate the end-member states and create theoretical spectra. So when the observations are made, you can match up those transmission spectra with theoretical models and say, well, if my spectra looks like this and has these gases at these strengths, it's probably this type of world or that type of world. So that's our goal, and has been our goal in preparation for observations made with James Webb and other instruments coming. So for GCM modeling, for these 3D climate models, it's expensive. It's much easier said than done. So a typical climate model has a million or more lines of computer code. They're developed for many decades by dozens to hundreds of scientists at labs, and they're all developed for Earth, and modifying them to simulate extrasolar planets is and has been a big challenge for different groups, and they're very expensive. So they take each simulation takes about 10 to 100,000 core hours. A core hour is one computing core running for 1 hour. So a typical, consumer MacBook Air, for instance, may have 4 cores. So we're running these things on supercomputers with a few hundred cores at a time and run them for days. And that's how we get up to these large numbers. So we have to be judicious with our use with these models. We have to leverage lower dimensional models, use sparse gridding techniques. We can't just if we're going to study a planet, a target, we can't just do a brute force approach and run 1,000 different simulations for the possibilities. We have to set up 30 different simulations and pick n number points and try to bracket what we think the planet might be like and go from there. As we move onward, we have to think about, well, what are the best targets? So it has to be for terrestrial planets, because terrestrial planets they're difficult to see. They're small relative to their stars. They're challenging for us to observe. They're cool relative as well. When you have 1,000 Kelvin hot Jupiter, you see it in transmission. You can also see it in an emission because it's so hot, but it's not so for a habitable zone planet. So it turns out that M-dwarf systems are the most compelling targets. So nearly 70% of the nearby stellar population are M-dwarfs. M-dwarfs are the smallest and they are the dimmest planets. They are the planets that orbit them are on very short periods. So this gives us numerous advantages. So because the planets are small in transmission, so as the planet eclipses the star, an Earth-sized planet is much relatively bigger compared to the size of an M-dwarf, so it casts a larger shadow, and the signal is larger from the planet. Because the M-dwarfs are so dim, a planet in the habitable zone must be their systems are scaled smaller, and planets in the habitable zone, which receive the right amount of energy, are much closer to the star. So they'll orbit once every 6 to 20 days. So if you're looking to observe a terrestrial planet around a sun-like star, it only has that eclipse, that transmission spectra, that transit every 365 days. Where in the TRAPPIST system, for instance, the famous planet TRAPPIST-1e is once every 6 days. So you you accumulate a lot more data a lot quicker, and the data is a lot better because the planet is relatively bigger and brighter relative to these dim stars. And it works both for detection and also for characterization. So we've been able to, if the hot topic recent discoveries, Proxima Centauri b, the TRAPPIST-1 system, LHS 1140b, and there's been others that haven't updated this since, have all been terrestrial planets around M-dwarf stars. So these are our best shot at observing a habitable planet in the next decade. And these systems are so alien that there's actually very interesting, I shouldn't say much more interesting, I should say the physics and dynamics of these planetary atmospheres are just very different from thinking about an Earth twin around a sun twin. So the one interesting thing, which again is to our benefit as far as modeling and characterization, is tidal synchronization. So like the moon, as I said before, like the moon is tidally locked with the Earth. The same side of the Earth always faces the moon. The same side of the moon always faces the Earth. Planets in the habitable zone around these M-dwarf stars have to be so close to the planet, and the systems are so much more compact that the planets are believed to be in tidal synchronization. So the same side of the planet always faces the star, and that controls the rotation rate of the planet. It revolves, the planet spins once every orbital period, so that helps us with modeling of these worlds. And it just leads to very interesting consequences because the dynamics of the atmosphere are heavily intertwined with the rotation rate. And you also have these different spatial variations of the solar installation. You have one permanent day side and one permanent night side. So that's led to this construct of the so-called eyeball climate, where you can have a habitable day side, but a night side is actually encased with ice. Another interesting thing is that the M-dwarf spectra, they're so much different. They're very much redder than our sun. You can see here, not normalized, but the sun spectra at 1 AU, so Earth, the spectra the Earth receives in black here. And then the spectra that Proxima Centauri b receives at its distance here. Now the fluxes are different, but even normalized, you can see that the peak flux for Proxima Centauri b is in the infrared. And the albedo of things is much different in the infrared. For instance, we know that snow is very bright on a sunny day, because all the energy is reflected. But snow is actually highly absorbing in the near infrared. So you don't have that effect in climate for planets around these M-dwarf stars. Snow actually will absorb the energy and heat up and melt away much more rapidly. And then chemistry is also greatly affected also, and the bottom plot shows the ultraviolet wavelengths. There's more near UV from the sun, but enhanced far UV from these M-dwarf stars. And the M-dwarf stars tend to be more active as well, much more violent stellar flares, things like that. So you have different chemistry, you have different climate, different dynamics. They're just very alien worlds. And these are going to be the first Earth-like planets we're going to be observing. So another consequence that comes out of first principles modeling is that when you have all the sunlight coming in the one side of the planet all the time, that permanent day side, you can think about it like the tropics on Earth, the convective storms on the tropics on Earth. But now imagine that the sun never sets. So you just have the constant summertime tropical convection occurring on one side of the planet. And combined with rotation rate effects, these planets are predicted to be very, very cloudy on the day side, these strong convective clouds occurring on the day side, which will give these planets a very high albedo, on the day side. And then you can have scenarios where as I showed before, ice is entirely confined to the night side and won't have very much effect on climate. So these tidally locked worlds around M-dwarfs, which are our best places to look for Earth-like planets, are just very, very weird compared to Earth. So there's been a lot of people who have done modeling of these worlds, and so I'll just show some quick modeling movies. So on the left, we show clouds at the bottom and then water vapor on Earth compared to an M-dwarf. So you have the sun would be shining right at the middle of this panel. You end up with these gigantic convective columns that span almost an entire hemisphere on these slow rotating Earth-like planets around M-dwarfs. So they're just very, very different. And then it even depends upon the rotation rate as well, that if you change the rotation rate from something that's very slow on the left to faster and faster, so the faster rotators are the ones that are 7 days, 4 days, it's more like the TRAPPIST system and things we're going to be better at observing. You just see very unique cloud patterns compared to what is seen on Earth. And then the top is also thermal emitted light as well, which thermal emission, measuring the thermal emission of these planets as they complete a full orbit is something that is very effective at helping characterize the climate of these worlds. However, it does remain to be, continue to be very challenging. And then as we continue our modeling odyssey, we can think about things that are very more different than Earth, so deep atmospheres and hot planets. These are simulations of, there's a planet called K218b, which is perhaps more mini Neptune than it is super Earth, but that's certainly going to be a target of JWST. Probably not, I shouldn't say probably, definitely not habitable. Even though it's in an Earth-like flux, does fall into the mini Neptune category. So no solid surface, you end up with this dense atmosphere. We found water vapor and clouds in the atmosphere, but no real surface, as the atmosphere just gets denser and higher pressure as you go down and down and down into it. But it still will be an interesting target for us to observe and compare against our models. And then we can also envision with our models, this is just for fun, volcanic eruptions on extrasolar planets where you get a plume of, a plume of energy, a plume entering into the atmosphere and persisting, which can actually change the composition of the atmosphere. So these tidally locked planets like Io, for instance, the tidally locked moon, will probably be highly volcanic as well due to strong tidal forces due to their close orbiting with their host star. So through modeling, we've able to come up with a definitive habitable zone, or our search zone, of where to look for different planets. Here we have as a function of the starlight received by the planet. It's my preferred unit rather than distance, versus the type of stars from the M-dwarfs all the way up through F-dwarfs. We don't tend to look for the bigger, hotter stars. You run into numerous problems when thinking about searching for planets. One, the stars become so bright that the signal for planets is just minuscule. And two, the lifetime of for larger and larger stars, and the star that burns half as bright lives twice as bright, lives half as long. So if we think about Earth, where it took 4.5 billion years for humans to evolve, and the Earth and our sun will live for about 10 billion. When you start getting into F dwarfs and hotter, the lifetimes of those stars goes down so rapidly that they're just not great targets if we're looking for a planet systems that are stable long enough for life to exist, or to develop rather, where M dwarfs are the smallest and dimmest of stars, will be around forever. So there's a lot of time for life to develop there. So of course, this is a simplified version of this habitable zone. There are other complications not shown in the plot, but which we've thought about, adding different greenhouse gases, not just CO2, but hydrogen or methane, things like that. Different background gases, so different amounts of nitrogen or oxygen, different surface types from land planets to aquaplanets. Different rotation periods has an effect, different planetary masses has an effect. There's uncertainty amongst the models. So you can think of these boundaries more as fuzzy boundaries. So, but again, as we're thinking about the habitable zone, it shouldn't be an argument of like, oh, well, the line is here or the line is there. More so, it's the search zone we're defining that has fuzzy boundaries. So, and lastly, I'll finish up with the TRAPPIST-1 system, which is, you're going to be hearing a lot about the TRAPPIST-1 system as time goes by with James Webb, because the TRAPPIST-1 system is definitively the best target system to study terrestrial worlds. And it was discovered in 2017 with a telescope called the TRAPPIST telescope. It was the first system found, and it was all this excitement of, oh boy, like this is TRAPPIST-1. We can't wait for TRAPPIST-2, 3, 4, 5, 6, 7, 8. Well, there's still just TRAPPIST-1. It stands out that significantly as a special system for us to study. So there are, so it's 39 light years away. So that's relatively close. There's 7 terrestrial-sized planets, all of which are transiting, and we know very accurate from follow-up measurements, very accurate geophysical measurements of the mass, the radius, the density, the period. They're tightly locked. We know the rotation, we know the stellar flux, we know the stellar spectra. We know all these quantities very, very well. And the star, TRAPPIST-1, is very small. So it makes for a very amenable target for study. So as I said before, James Webb wasn't designed to study exoplanets. It was designed to study galaxies and all sorts of other stuff. And exoplanets wasn't even a thing, wasn't even a thought. And we're retro-purposing it for exoplanets. And then even further down the line, terrestrial planets are the hardest to get at. But the TRAPPIST-1 system will be the one where a lot of telescope time is devoted to studying this system, because not only can we study habitable planets, but we can study the comparative planetology of a full system of planets. So all the radii of the planets are all in that terrestrial wheelhouse from 0.78 to 1.14 Earth radii, the masses from 0.33 up to 1.116 Earth masses, and the stellar fluxes range from about 4 times the Earth flux to about 14% of the Earth flux. So we have this very nice range that goes from hot planets to temperate planets to very cold planets. So the conventional habitable zone would be right there on the screen. So TRAPPIST-1e, I'll call it the editor's choice. It's smack in the middle of the habitable zone. Models of all sorts of everyone's models agree that there's such a wide range of conditions that TRAPPIST-1e could maintain habitable conditions for, that it could potentially be durably habitable for a variety of different assumptions. TRAPPIST-1f needs a dense atmosphere. That would be sort of your early Mars analogy. You need a dense CO2 atmosphere to stay habitable. If you want to kind of loosen it up a little bit, you could maybe even include TRAPPIST-1d if you assume it to be a dune-like planet, a water-limited planet, so that wouldn't allow it to go into a runaway greenhouse. Maybe you can have pockets of habitability if it's mostly dry with trace amounts of water vapor in it. And then B and C, hot Venus analogs. G and F, probably icy moon-like analogs, Europa and Titan-like. So in totality, we have this in, one, I didn't include this on I should have though, the periods of these go from about 2 days for planet B. TRAPPIST-1d is about 4 days, E is 6 days, H I think is around 20 days. So short periods, you can collect a lot of point web there and collect data on all the planets all at once effectively. So it's going to be a very interesting planet for observers and theoreticians to study. So I'll switch back for a second to, so remember from the beginning, WASP 96b, the spectra produced. So this was from a single transit. It was about 2.5 hours of telescope time. It was cherry picked for first release because they knew had relatively few clouds, which clouds impede our ability to get good spectra. We knew we'd be able to get a good spectra in a very short time commitment from the telescope. Thus, early release data from it. TRAPPIST. So this is from theoretical calculations from JWST Jaegers, a scientist at Johns Hopkins, and many other people have duplicated. It's TRAPPIST is a the system of study, so many people have duplicated this. This is theoretical calculation. All the dots are instrument sims of what we think JWST will be able to do. This is for TRAPPIST-1e for various different CO2 climates and water vapor climates and clouds. And the problem is, so for TRAPPIST-1e, could take dozens to hundreds of transits to get data comparable to WASP 96b. So you're not talking 2.5 hours of time. One transit, now you point it away, but you're talking many telescope hours from JWST. So to do even the best of systems for terrestrial planets is a large commitment of telescope time. And it's not just the time to time looking with the scope on, looking at the transit, but there's also and I'm not an observer, other people would know better than I, the time to move the telescope around and optimizing where they're pointing the telescope and the grant process of getting telescope time and organizing it all. So they won't just point it at TRAPPIST-1 and leave it there, but they'll point it, get a transit, then somebody else will get the scope pointed away, then they'll spool it back and whatnot. There was a complicated process, and it's expensive to do the habitable planets with JWST, but there's still hope. And so TRAPPIST is the system that they're going to be dedicating time towards. So, as I said, so the TRAPPIST system will be the system. There's hopes of being able to characterize the system. It's doubtful that we're going to be able to make bold claims, and I would refrain from them. But even just so modeling studies have shown, we should be able to tell if planets have an atmosphere or not. And that may sound like a minor thing, but it's not. If we are able to see CO2 lines, it's going to be the easiest thing for us to see on any of these planets. That'll tell us a lot about how the active M-dwarf stars, which tend to strip their atmospheres away of the planets, interact with the system, and that would be itself a very big finding, just to see a signal from CO2. on these planets. So clouds are always sort of the nemesis of observers. As a modeler, clouds are extremely interesting. Flat spectra would indicate clouds in the atmosphere, which are kind of vexing, but also interesting to hint at condensates in the atmosphere. We may be able to see water vapor, but that's really going to be dependent upon how the cloud structures come into play. Methane is also a possibility. There are different slices of parameter space that are more amenable to seeing different gases. So one of the, what's the right word? It's not a paradox, but perhaps just a frustration is that habitable climates lie at this nexus of being hard to observe, because you look at the Earth, there's a lot of water, but there are a lot of clouds. So for a habitable planet with a lot of water, there will be a lot of clouds. So habitable planets will have clouds, and clouds make it harder to observe the gases beneath the cloud layers. Where in the different, colder regimes or drier regimes, it'll be easier to see things, but it's the habitable planets will hide their secrets well from us. So still, I'm hopeful that, like with Hubble, through the years with JWST, very resourceful and ingenious observers will be able to squeeze the most out of it and do more with JWST for habitable planets than we think coming into it. So I am hopeful that the information we're going to get back is going to be not just revolutionize the science of hot Jupiters, but also it will revolutionize the science for terrestrial exoplanets as well. And the TRAPPIST-1 system is going to serve as a starring role in that. So with that, I will end my talk, and thank you all for staying late with me. And I'm happy to answer any questions.
Well, thank you, Eric. Thank you very much. This was a very comprehensive and detailed presentation, so we very much appreciate. I'm sure there are some questions. I will start with my question. Okay. We talk about exoplanets a lot. What about exomoons? The discovery of exomoons, whether they could be in a habitable zone if the planet is not, or vice versa. Do you have any view on these exomoons?
So people have thought about exomoons, but they're incredibly, incredibly hard to definitively detect, let alone characterize. I've seen a few speculative papers on theory behind how their atmospheres might be affected by the neighboring planet and whatnot. They're certainly there. We found Jupiter-like planets at an Earth-like stellar flux, and you can extrapolate that there's probably moons, and the moons could be habitable, but it becomes even more complicated to make that observation, because now you have the moon circling a planet and the planet circling a star, and that we're getting signals from the planet and the moon and the star, and variability from the star, which I didn't even talk about, which is a complicated thing. So I certainly there are habitable exomoons. We're going to struggle enough just to characterize individual standalone planets, let alone exomoons. So it's an interesting topic, but it's exceedingly difficult to get good observations of.
Question from, I think, Dina, asking how we get data from James Webb.
That's a good question. So I don't use I could shoot off an email to a colleague who'd give me the answer. I am a kind of a modeler through and through. So I don't use James Webb data directly in my own research. It's publicly available. Probably through the Space Telescope Institute. But yeah, I'm sorry I don't have a more direct answer for you, that because it's in science we're so stovepiped into our specialization. I am like the modeler guy, and then I interact with a lot of observers who will be dealing with the data, but I'm up to my ears in the models. So I ask others to get the data and interpret it for me.
You mentioned the extensive amount of observing needed for TRAPPIST-1. Ron is asking, any idea yet on how observing time on JWST will be divided among, say, exoplanets versus distant galaxies and other targets?
Yeah, so that's I wish I could give you more information. That is certainly a fight that I have an ear on from my colleagues who there's been a big arguments in the field as far as, well, how much should we put the exact question. So people who are interested in distant galaxies and other targets are somewhat angry that exoplanets are sort of the new kid on the block, and JWST was designed with thinking about looking at galaxies, distant galaxies in mind. So why are we going to waste all this time, not waste, but use expensive time on things it wasn't designed for versus using things in a wheelhouse for galaxies? So that's, I think, a continuing debate about how much time is going to be divided between three. Exoplanets are certainly going to get their fair share, but they're not going to dominate, just from that very reason that there's other science to be done in the universe outside of extrasolar planets. And so, yeah, I don't know the exact breakdown, but that's something that will get argued in each different proposal or each different observing time round. So they just went through the cycle ones, and I don't know when the cycle twos are being solicited.
But the fact that they had a Jupiter-like data as part of the cycle one indicates that there will be some time allocated.
Yeah, so there's guaranteed time already for do the TRAPPIST system, and there's guaranteed time for hot Jupiters as well. That it's even an argument within the exoplanet science community of how much time should we be spending on habitable zone planets when we know that JWST is not going to do that. It'll do a better job than anything else, but it's going to do amazing science for hot Jupiters. For terrestrial planets, there's a high likelihood of being frustrated and spending lots and lots of the time. So I think it's still up for debate and up for, as each incremental piece of science comes through, how the next cycle will be allocated, and the cycle after that, and the cycle after that. So we'll see how it goes. But I think for cycle one, there's been guaranteed, they've tried to be even amongst terrestrial, some for terrestrials, a lot for hot Jupiters, for galaxies and other things. And I think that'll evolve as the science comes back.
There is an interesting question from Greg Larson. How many planets in our solar system could be detected from a distant observer using our current technology? This is a bit hypothetical, of course.
Yeah, that's a good question, though. I'm going to speculate that a distant observer would likely see, they could see Earth. That's a possibility. We have seen, I didn't bring it up, there was a system, I think it's Kepler 62, it's about 1,000 light years away, where it's almost a little bit brighter than the sun. And we found an Earth-sized-ish planet, maybe 10% bigger and a little 10% further away. So it's possible that using our current technology, that was with Kepler, we could detect Earth around a sun-like star within about 1,000 light years. So that's definitely possible. Smaller the planets, a little harder it goes. Certainly Jupiter and Saturn. But the problem again with Jupiter and Saturn, for instance, with our current technology, is their orbital periods are so long that they would have, for Kepler, I think they needed three. I think their rule of thumb was 3 or more transit detections in a periodic fashion in order to confirm that it's a planet. And within the lifetime of Kepler, they would not get 3 transits of Jupiter around our sun, or 3 transits of Saturn or Uranus or Neptune. So within that time frame, they probably fortuitously would have seen Earth, and maybe they would have seen evidence of larger planets, but if they had the same criteria of us, maybe they got one transit. Maybe if they're lucky, they got two at the very beginning of Kepler and the very end of Jupiter, but they, based on our criteria, they would say, well, that's not enough. We're not sure. We only got two transits. We didn't get three. So there's a time limitation as well.
Another interesting question from Steve. Okay, let me. Okay, I cannot read it here. How would plant life differ on a planet around an M-class star, as opposed to a G-type star, such as the Sun, due to the difference in the spectrum?
Mm-hmm. So yeah, there's been other people, a colleague of mine, Nancy Kiang, she studies this exact question. I wish she was here, she could answer it for me. But as you astutely put out, that are posited, photosynthesis would have to act on completely different wavelengths. There's just not enough energy coming in the visible to operate on photosynthesis, for photosynthesis to act the same way. Now, I think it would be arrogant of us to assume that it just couldn't happen if the spectrum on an M-dwarf planet where all the energy was coming in the near infrared. I guess I optimistically feel like life would adapt and find a way to use the wavelengths given to it to be able to operate, and it would have to be able to do that in the infrared. It wouldn't look like photosynthesis as we know it now. As far as I vaguely remember biology and what was it, ATP and whatnot, and for photosynthesis, those chemical reactions may be completely different. But I think to say that it couldn't happen, I think would be arrogant of us.
Jim Wallace is asking, if you have the clouds, and you mentioned the clouds as the problem, can you differentiate H2O, CH4, NH3, and so forth?
So indirectly, yes. So the problem with clouds is they result in a featureless spectra. So you end up with, whether it's H2O or methane droplets or ammonia droplets, little spherical particles that scatter light similarly in a diffuse manner, like if you go outside on a foggy day and how everything looks gray, right? So you end up with this flatness of spectra. Now we can deduce what the clouds may be based on the context. That, like with the WASP 96b spectra that was shown, or K218b, which I didn't really talk about, which is another hot target, but it's more of a Neptune class planet where we've seen water. So if we see flat spectra with little tiny peaks of water coming out, little water lines coming out, we can kind of make that deduction combined with where the planet is in the system. So the condensation temperatures of water, methane, and ammonia are very different. So on Titan, for instance, out at orbiting Saturn, it has an active methane cycle like we have an active water cycle. And I forget off the top of my head what the condensation temperature is of methane, but on Earth, we're way much too warm for methane to exist in all three phases on Earth. And likewise on Titan, it has rocks, and the rocks are made of water ice because it is so cold. So in that context, if we observe, say, TRAPPIST-1H, for instance, it's been posited it could be Titan-like. So if we observe clouds on Titan, these flat spectral regions and little pockets of methane lines poking up above the flat spectral regions of the clouds, we could indirectly posit that those clouds must be methane, for instance, methane or ammonia, for instance, based on the other spectral content and its place in the distance from the star. So I guess the short answer is, taken individually, we can't tell the difference based on the flatness of the spectra, but taken in context of the bigger picture, we can imply what the clouds are probably made of.
Greg Fogarty is asking a question or making a remark, I guess. There must be many more systems out there that cannot be detected by the transit method when they are presented to us face on versus edge on.
Yes, that's a extremely good point. And more people are wanting to do detections of non-transiting systems are made by radial velocity. So you can see the wobble of the star, and you can still see those for non-edge-on systems. But then to characterize those planets, it becomes, you have to rely on thermal emission. So that the thermal emitted light from the planet against the star and how that changes as the planet goes through its orbit. So it's a harder detection, particularly from habitable zone planets, which are cooler and we don't emit that much thermal radiation compared to the parent star. But that's a very active area of which people are trying to do better, because that will open up many more systems to study rather than limiting us just to the transiting systems. But it's harder. Transiting, it's easier to do analysis and characterization through transit spectroscopy than it is through emission spectroscopy. So we're working on it.
Chris Whalen is asking or making a remark, I guess. O2 is extremely reactive and isn't expected to have a naturally very long life in an atmosphere without life. One, can we detect O2? And two, if we did, wouldn't this almost be a guarantee of life?
So we can detect O2, but unfortunately, two, it's not a guarantee of life, because there are certain pathways at which you can have, and there's literature out there if you Google false positive biosignatures, so different permutations of things we think of as biosignatures like H2O, O2, methane, that you can produce them in atmospheres from non-biological means. So with O2, one of the big ones is, so the runaway greenhouse process, as a byproduct, you end up building up a whole bunch of oxygen, abiotic oxygen in your atmosphere, because you get all this water in your atmosphere, and then the water molecules are split. So the H is split off from the O. The H2 is split off from the O, and then the H is so light it'll escape the space, and then the O2 is recombined. So you end up getting all this abiotically produced oxygen. So when I think about biosignatures, there's never going to be 100% guarantee unless we get a message like in the movie Contact. But we think about the O2 and methane combination together is one that is very attractive for biosignature, because those two gases are not expected to be stable together unless you're producing O2 and producing methane through these, through what we believe are biological means of photosynthesis, and then early life on life on Earth today, but also early life for methane producers as well. So you need a constant source of each of those, because O2 and methane destroy each other. So, and there's different permutations as well in a rich field about biosignatures. They're false positives, and also what we typically try to look for combinations of gases, not just any singular gas, because almost any singular gas you choose, you can posit some sort of physically plausible abiotic production mechanism for the gas, and O2 is the same way.
Okay, Eric, this has been a very educational and informative presentation. Do we have any other questions before I conclude? Are there any other questions? If you do, raise your hand, or oh yeah, I have. Okay, there are some thank you messages, and people are saying they thank you very much, Eric. Everybody is very appreciative. So thank you. We can probably stop the live streaming at this point, Dina.